In this video, we will work 5 problems similar to the section 5.4 diagnostic problems. Section 5.4 is on the fundamental theorem of calculus. It's an important sounding theorem. It is important, and it has 2 parts. So we're going to look at part 1 first, and then we'll do 2 problems. And then we'll look at part 2 second, and then we'll do a few problems after that. What this theorem says in a nutshell is that the definite integral and the derivative are in some sense opposites of each other. In a similar way that multiplication and division are opposites, or addition and subtraction are opposites, the process of finding a definite integral and the process of finding the derivative of a function are in some sense opposites. And to see what this means, let's look at the theorem and look at some examples. So in the fundamental theorem of calculus part 1, we begin with a function lowercase f. And we're doing a couple of things to f. The first thing we're doing is we're taking an integral of f, and then we're taking a derivative, and the conclusion basically is we get back to where we start if we do that. If we start with this lowercase f as our function, integrate and then take the derivative, and this is what I meant when I said they're opposites. The derivative undoes what the integral does in some ways. But let's look more closely at this. Inside, when we take the definite integral of this thing, we're integrating from a to x. And here a represents some number, and x is a variable. So this is a function of x, and this is the function that the theorem calls uppercase f of x. So the variable is the upper limit of integration. T is not a variable. T is what we can call a dummy variable. If I take the integral of f of t dt, it has the same value, means the same thing as if we take the integral of f of z dz or f of w dw. So f of whatever d whatever means the same thing no matter what variable we use there. So the t really doesn't matter. The variable is x. And then when we turn around and take the derivative of this function, the result of that is the same as if we just take x and plug it in for our dummy variable. So if we have f of t dt, we integrate from a to x. That's a function of x. When we take the derivative, we get f of x. We can think of this as a new rule for taking derivatives. If we have a function defined in this strange way where the variable is an upper limit and we want to take the derivative of this function, the rule says just plug in that upper limit. Let's look at an example. So here we have y equals the definite integral from 1 to x, and we're integrating the square root of sine theta plus cosine 2 theta d theta. Now the long way to do this problem would be to actually evaluate this integral using the definition of the definite integral. And when we did that, the result would have x in it, because that's the upper limit. And then we could turn around and take the derivative of that with respect to x. That would be a very long, hard process, and the fundamental theorem of calculus gives us a huge shortcut. We're going to use that rule we just saw. This is set up the same way. To take the derivative, we're just going to take our upper limit and plug it in for our dummy variable, which in this case is theta. So we're taking the derivative of y, x is our variable, so this is dy dx, and it equals the square root of sine of x plus cosine of 2x. So using the fundamental theorem of calculus part 1, we can make quick work of this. Problem 2 looks similar, has a key difference. Y again is defined in terms of a definite integral from 2 to x to the 8th. So that's the difference here. Instead of just having an x sitting in the upper limit, we have x to the 8th. Here we're integrating e to the square root of t dt. And again, we want to find the derivative of y with respect to the variable x, because x is the variable on the right side. Again, t is a dummy variable. And we'll just use that rule again. We'll plug in this upper limit for the dummy variable, and we will get e to the square root. When I replace t with x to the 8th, this is what we get. Now in this problem, we're not done. There's another step. And so this is a new rule for taking derivatives for functions defined this way where the upper limit is a variable. But we have to use this, we still have to use all the other rules of derivatives that you've learned. And here we need to use the chain rule. And the reason we need the chain rule is that we have a function sitting inside of another function. We can look at it that way. We have this function x to the 8th sitting in this other function, which is the integral from 2 to the variable e to the square root t dt. And so you want to remember that when you have a function, we'll think of f of x as being like x to the 8th. When we have a function sitting inside of another function and we take the derivative of that, the chain rule says first we take the derivative of the outside function and the inside stays exactly the same. But then we take the derivative, secondly, we take the derivative of the inside function and multiply by that. So we have to remember to multiply by the derivative of what's inside. So here we're not done. We took the derivative of the outside function using the fundamental theorem of calculus part 1, plugging in that upper limit. But now we have to multiply this by the chain rule times the derivative of x to the 8th, which is 8x to the 7th. We can simplify this a little, and I'll rearrange it too. This is 8x to the 7th, e. The square root of x to the 8th is x to the 4th. The square root can be thought of as x to the 8th to the 1/2, which gives us x to the 4th. That's it. That's the derivative of this function. Let's look at part 2 of the fundamental theorem and some examples following that. Part 2 of the fundamental theorem of calculus is by far the more common version that you'll see. What this says is, again, we start with lowercase f. Here we're integrating it from a to b, where a and b are both numbers. And this theorem says if we want to evaluate a definite integral like this, we can use an antiderivative. Uppercase f represents an antiderivative of lowercase f. So to evaluate a definite integral, we can use an antiderivative. And for this reason, we often use the words antiderivative and integral synonymously. They're interchangeable sometimes, but that's because of the fundamental theorem of calculus part 2. So if I want to evaluate an integral, what we want to do, a definite integral, we first need to find an antiderivative and then evaluate it. First we evaluate it at the upper limit, b, then we evaluate it at the lower limit, a, and we take the derivative, the upper minus the lower. So let's look at the next problem, problem 3. It says evaluate this integral from 0 to ln of 4. Those are both numbers, and what we're integrating here is 8 e to the 2x dx. So what we want to do is find an antiderivative and then use that to evaluate. One thing we can do before we begin is take the 8 out of our integral if we like. It's always a good idea to simplify the integral before evaluating it. Now we want an antiderivative for this thing. And we should remember the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x. But if we take the derivative of e to the 2x, we get e to the 2x times 2 by the chain rule. So taking the antiderivative, we will have e to the 2x times 1/2. We have to put a 1/2 there. That's the antiderivative of e to the 2x. And this came up in section 4.8. That was on antiderivatives. So if we know the antiderivative of this function, then we can use that to evaluate the definite integral. We're going to evaluate this as x goes from the lower limit, which was 0, to the upper limit, which was ln of 4. And that's what this notation means. First, we plug in the upper limit. This is 8 times 1/2. I'm just going to write that as 4e to the 2. And the upper limit was ln of 4. So we're going to plug that in for x first. And then we plug in the lower limit and we subtract. 4e to the 2 times the lower limit was 0. We plug those in and evaluate. E and ln are opposites. They're another pair of opposites. And so E and ln cancels, one way to look at it. If E and ln are right next to each other, they cancel each other out. But they're not right next to each other because we have this 2 in the way. So what I'm going to do to simplify my answer is I'm going to use a rule of logarithms. I'm going to take this 2 and bring it in as a exponent inside. This equals 4e to the ln of 4 squared, which is 16, minus 4 times e to the 0. And here now the e and ln cancel out. The ln is the natural log. It's the log base e. So if I take e to the ln of 4 squared, we get 4 squared. This is 4 times 4 squared minus 4. E to the 0 is 1. So this is 4 cubed, which is 64, minus 4. It's 60. So the value of this definite integral is 60. Let's look at the fourth problem. Another integral to evaluate. Definite integral, meaning we have limits. We have a lower limit and upper limit. This one involves a trig function, and so we want to recall secant square of t, that's the derivative of something. And to evaluate this integral, we want to use the antiderivative of this. The antiderivative, so we're looking for a function that has secant squared as its derivative. And here, we could just use memory. We want to remember that the tangent, the derivative of the tangent is secant squared. So tangent of t is the antiderivative of secant squared of t. And if we recall that fact, then we can use the antiderivative to evaluate this definite integral. We're going to evaluate this as the variable t goes from pi fourths on the lower side up to t equals pi thirds in the upper limit. So this is tangent of pi thirds minus tangent of pi fourths. And now we can evaluate these also. And you can use a calculator or memory. I'm going to just recall the unit circle quickly here to evaluate these. And this should be familiar. And these values for the angle should be familiar also. Pi fourths comes through at pi fourths is 45 degrees. At pi fourths, the sine and cosine are the same. They're root 2 over 2. So there, the tangent of pi fourths is 1. Pi thirds is 60 degrees up here, and if I want to know the sine and cosine of pi thirds, you should remember the numbers square root of 3 over 2 and 1/2 should be familiar signs and values for sine and cosine. And here, if we think about it, because pi thirds is 60 degrees, the x-coordinate is shorter than the y-coordinate here. And the x-coordinate is the cosine. The y-coordinate, the square root of 3 over 2, is the sine. So the tangent of pi thirds, if I'm thinking it through without a calculator, tangent of pi over 3, that's the sine of pi over 3 over the cosine of pi over 3. That's the square root of 3 over 2 over 1/2. The 2's cancel. That's the square root of 3. So our final answer here, this is the square root of 3 minus 1 is the answer. The tangent of pi thirds is square root of 3. The tangent of pi fourths is 1. We take the upper limit and subtract the lower. One last problem, and it's just phrased in a different way. I don't see an integral here, but if I read the words, I'll see it's asking for an area. Find the total area of the region between the curve and the x-axis. That is a definite integral. We want to integrate this from 1 to 3. It's a good idea to look at the picture first to see what it looks like. Here's a graph of this function. This is the one in red. So here's a picture of what we're looking for. The function goes all the way up past 20 on the right. On the left, it's down at 1. The width of this interval, we're going from 1 to 3, is 2. So without doing much work, I can see that the area we're looking for under the curve is less than 20. And we maybe, so less than 40. this rectangle is 20 by 2, that's 40. So, and it looks like it's less than half. So I would say this looks like this area we're looking for. And we don't have to draw the picture, and we don't have to guess at this answer either. We can find the exact area of the shaded region using the fundamental theorem of calculus, and that's what we'll do. So one reason to look at the graph is to see if it dips below the x-axis anywhere. We'd want to consider that if it did. Because if they're asking us for an area, area is always positive, but if it goes below the x-axis, the definite integral is negative. So that doesn't happen here. And also, when we get our answer, we should be able to assess whether it's reasonable or not. So the answer is some number less than 20. Let's see what we get. By definition, this area we're looking for is the definite integral from 1 to 3 of x cubed minus 2x plus 2 dx. And the fundamental theorem of calculus says to find this definite integral, we can use antiderivatives. And to find the antiderivatives here, we're going to use the power rule. The antiderivative of x cubed, we're doing the opposite of taking the derivative. So we're going to add 1 to the exponent and divide. So the antiderivative of x cubed is x to the 4th times 1/4 minus 2x squared, but then we divide by 2. The antiderivative of 2x, the antiderivative of 2 is 2x because the derivative of 2x is 2. So this is an antiderivative, and we can check that by taking the derivative and see if we get back to where we started. I'll simplify this a little bit. This is x to the 4th over 4. This is just minus 1. This is minus x squared plus 2x. And we want to evaluate this as x goes from 1 on the low side up to 3 for the upper limit. And now it's a calculator problem. We'll plug in the 3 first. We get 3 to the 4th over 4 minus 3 squared plus 2 times 3. And then we subtract 1 to the 4th over 4 minus 1 squared plus 2 times 1. And just have to be careful with the plus minus signs and that sort of thing. But 3 to the 4th that's the same as 9 squared. This is 81 over 4 minus 9 plus 6. I'm going to distribute this minus through. So I have to be careful about plus and minus signs. But this is minus 1/4 minus a negative. That's plus 1 minus 2. Of course, you could do this in different orders. But I'm going to combine these two. 81 over 4 minus 1/4. That's 80 over 4, which is 20. Minus 9 plus 6. I'll combine these two. That's minus 1. So what we have is 20 minus 9 plus 6 minus 1. This is 26 minus 10. It's 16. And of course, you could have pulled out a calculator and done it on your calculator here also. And 16 looks reasonable. Less than 20. The area of this yellow shaded region is exactly 16.